Hello there. In this video we're going to do an example of a difference of means test using an application that you may be able to relate with. So suppose that you own a company and you want to test the effectiveness of some training module on your employees. Before and after the module, you collect some results. So let's assume you take 5 people, you measure their performance, say in the workplace, before the training, and then after the training you measure their performance in some way, record your results before and after. So based on these results, is there evidence to support that the training module had a significant effect, either positive or negative? Hopefully positive, right? Alright, so how are we going to perform a hypothesis test on this type of scenario? So I'm going to label the pre-training as set A and set B. So A and B correspond to populations, and 1 through 5 correspond to samples from these populations. So pretty much what the null hypothesis, or one null hypothesis that you could say, is that mu A is equal to mu B with a two-sided complementary alternative of mu A does not equal to mu B. So of course we're going to approach this in the same exact way as before. We're going to define mu D. Let's define it in the backwards direction, say mu B minus mu A, since we see that most of the values in B are bigger than A. So from here, what will we have? So we're going to have that the null hypothesis H0 is that mu D is equal to 0, with the alternative that mu D does not equal to 0. Alright, so one observation is that A and B are related to one another, i.e. they are dependent samples. So since they are dependent samples, we're going to use a paired difference t-test. So this is the type of hypothesis test we're going to use on this type of hypothesis. Alright, so how are we going to begin? So we're going to begin by subtracting set B from set A. So we're going to do B minus A in this case. So 52 minus 45, that's going to be, let's see, what's that going to be? That's going to be 5, 6, 7. 25 minus 23, that's going to be 2. 96 minus 87, that's going to be 9. 48 minus 42 is 6, and 55 minus 50 is going to be 5. Alright, so once we calculate those differences between the post-training data and the pre-training data, then we can calculate the mean and the standard deviation of these values. So with these values, we get that the mean is going to be equal to 7 plus 2 plus 9 plus 6 plus 5. And that's going to be equal to about 5.8 once you divide that by 5. And then the standard deviation, so that's STd19 in Excel, of those numbers, that's going to give us about 2.588. So these are the statistics of the differences between the data values. Okay, now that we got those, now we can start to do things with them. So x bar d again is 5.8. Standard deviation of the differences is 2.588. Alright, great. So from here, what do we do? So let us assume we want to operate under a level of confidence of 0.95, which will imply that our statistical significance is going to be 5%. So from here, since our sample size is small, we're going to use a t critical value. So t alpha over 2 is going to be equal to, in Excel, t.inv of 1.95 divided by 2, comma, the degrees of freedom, which is the sample size minus 1. And you're going to find that this number is approximately 2.776. Alright, it's the t critical value. Alright, so from these things, then we can calculate our marginal error. So our marginal error is going to be equal to, again, the critical value times the standard deviation of the differences divided by the square root of the sample size, which is going to be approximately equal to 2.776 times 2.588 divided by the square root of 5, which is going to come out to about 3.213. So this is the marginal error for my confidence interval. So remember, the confidence interval for the mean difference, it has a point estimate of x bar d. So that's going to be the center of this confidence interval. So that means this is going to come out to, x bar d came out to 5.8 minus 3.2, let's round to one decimal place, and 5.8 plus 3.2, which is going to come out to, so 5.8 minus 3.2 is going to be equal to 2.6, and 5.8 plus 3.2 is going to come out to 9.0. And you'll realize that the rounding is not really going to make a difference here. This is a 95% confidence interval for the mean difference. All right, so what can we do with this? So recall that the null hypothesis was that the difference between these populations is equal to 0, and we are using the alternative that there is no significant difference between them. Or there is a significant difference between them, my mistake. All right, so how do we use this confidence interval to sort of test that hypothesis? Well, if there is no significant difference, that means 0 should satisfy this confidence interval. But we see that 0 does not belong to our confidence interval, right? 0 is not in between 2.6 and 9.0. So what does that mean? And there's a difference of about 2 from 0, so it's not necessarily a negotiable point. You may think it is, but let's just not sort of discuss that at the current moment. So that means, at least with regards to our confidence interval, we're going to reject the null hypothesis. So reject the null hypothesis. H0 mu A equals mu B. So what does that mean? So if we reject the null hypothesis, that means what? That means we have evidence to support the claim of our alternative hypothesis, namely mu A does not equal to mu B. So what does that mean? Well, that means the means are not the same. That means what? Well, in terms of our application, that implies that the training model, or the training module, had some significance effect. Now, caution, some words of caution here. This does not imply that the training model had a positive effect. And it does not also imply a negative effect. It does not imply either of these. The reason why it doesn't apply either of these is because we used a two-sided alternative, namely mu A does not equal to mu B. If you were to use an alternative, say mu B is greater than mu A for that one, or mu A is... So if we use these alternative hypotheses, mu B is greater than mu A for the positive effect, or mu B is less than mu A for the negative effect, then we could come up with those conclusions. But since we chose the two-sided alternative that mu A is not equal to mu B, the only thing we can say from this test is that the training model had some significant effect. But we can go back to our sample and realize all the values in B are bigger than A. So from our analysis, we can see that the positive effect is actually the one that's happening. But that's not coming from our hypothesis test, that's just coming from observation. But this hypothesis test at least proves that there is some significant effect for the training model on the employees. And that's how you perform a paired difference t-test.